All right. Chapter 7 Probability and Sample Distribution of Sample Means. Okay. So, this is a really interesting idea here. In this chapter is a lot of sort of conceptual stuff. We're going to learn a new equation today that's going to go in the denominator of our test statistic when we're looking for z-scores for now a sample of people as opposed to just one single score. We're also going to be exploring some things that are sort of rooted in math and statistics theory. But as long as you sort of understand kind of three basic principles of it that we'll, of course, go over throughout this lecture, you should be be able to sort of understand the gist of why this is important. Okay. So let's just start off with an example here to kind of illustrate this idea of distribution of sample means and why it's such a powerful concept in statistics. So let's say you want to study reaction times in response to pictures of kittens for everybody in the United States, which is a very noble goal. Ideally, you'd like to know the mean reaction times in response to cat pictures for everybody in the U.S. And how would you go about doing that? Well, one way you can do that is to measure reaction times in response to kitten pictures for everybody, right? Every single living adult, right? So you take the sum of their reaction times and you would divide that by the total number of adults in the United States, right? Is that practical? Well, it's a rhetorical question, right? Obviously, it's not practical, right? In order to find the true mean reaction time in response to cat pictures, you'd have to measure every single adult in the United States. You might say, well, look, I can't really measure everybody, but maybe I could take a sample, right? And I'm going to make every effort to make sure that that's a random sample, right? I don't just want to sample, 100 people who only really, really love cats or only 100 people who really love dogs, right? I want a random sample that should not be biased or skewed in any way. And then I can sample from that sample and I can get a mean and hopefully it's representative of the population. So much of statistics involves this concept, right? Generating a measurement from a sample and making inferences about the population. So up until now, when we've talked about distributions, we've been talking about distributions of individual scores, right? How this person compares to that person on the SATs, how long it takes a baby to crawl compared to another baby. Now we're talking about distributions of sample means, right? The sampling distribution of the means. So this is the distribution of all sample means obtained by selecting all possible samples from a specific size from a population. And this is intimately related to this idea of the central limit theorem, right? The central limit theorem itself describes the important characteristics of the sampling distribution of the means, right? So this is pretty cool. I'm going to illustrate how this works by using relatively easy numbers from a non-standard distribution, like what you see here in the slide. Now, this could be anything, right? It could be a sample of all possible test scores in a population. And that's what we'll pretend this is. Like, this is a sample of 4 possible test scores in a population. As you can see, it's not a normal distribution, right? If we were to take the mean of this, if we were to compute the mean, we would get a score of 3.8. And so what I'm going to do is take samples from the sample distribution, right? I'm going to average those samples, and I'm going to plot the frequencies of the averages that I get. Now, let me define something, right? I want to say, to begin with, just sort of illustrate this early on, I want to say that my sample size is 5. Now, I can use any number, right? But first, I want to start off with something small, right? So below my original distribution, right in here, right, is my first sample of sample size 5. So what I've done here is I've taken 5 scores at random from this distribution, and I've plotted them, right? Now, this is going to seem confusing, but try and understand that this is akin to sampling from a sample. This seems kind of weird. But when we talk about the sample mean and the sampling distribution, normally the sample refers to a set of samples from your distribution. Let's put it this way. There are about, at any given time, up to, say, a dozen statistics courses being taught in a semester, right? And we can consider that a population, right? All of the statistics classes that are being taught in the semester? Well, this class is a sample, right? This class that you're in is a sample of that population of classes, of samples themselves that are part of a statistics set. So if I randomly select 5 exam 1 scores from this class, I'm taking a sample from a sample. And the sample size, which would be 5, tells you how many I actually took from the sample distribution. So this bottom figure shows what happens when I randomly sample 5 values from the distribution up above. So I could keep taking samples of 5 test scores from my sample. So here's another one, right? And another one, right? This is, again, completely different sample. And another one, and so on and so forth, right? And importantly, I could plot each of the means of each one, right, of each one of these samples, right? I could find the mean of each one of them, right? And I could plot those as well, right? So I plot the averages of the 3 samples that I just selected, and it looks like this, right? Here's the mean of one sample, here's the mean of the second sample, here's the mean of the third sample, right? So these are the means, right, of each one of these samples that I took earlier, okay? Now, all I want to do now is keep taking these samples of sample size 5, from our sample, and I want to get the average of each sample that I take. I want to plot it. And let's say I do this 10,000 times. So I already did this in a statistical package that we call R, right? So this is me doing that 10,000 times. Taking a sample size of 5 from that original distribution, getting the average of each sample, and then plotting them in a histogram, right? And eventually what you get, if you start plotting all those samples from the original distribution of a sample size of 5, is you get something that starts to look like a normal distribution. So imagine each value in this distribution is an instance of sampling 5 test scores from our original sample and taking the mean of those 5 test scores, right? So this is sample size 5. Now let's say I did the same thing, but instead of just sampling 5 times from our original distribution, I take 30 times. So from that original non-normal distribution, I randomly take 30 scores out of that distribution. I compute the mean. I do that 10,000 times. Every time I compute the mean of a new sample, I plot it, right? So I take 30 samples. I get the mean of each one. I plot it, do it 10,000 times. Now, 2 things are going to start to happen. One, the histogram of these sample means is going to start to approximate a normal distribution even more, right? And 2, it's going to have a smaller standard deviation, right? A smaller standard deviation. Let's go crazy. Let's increase my sample size from 30 to 100. Look at this. So as your sample size gets larger, you approach even more of a normal distribution. But what's cool about this is that we can start with an abnormal distribution, right? Remember, we started with an abnormal distribution of just 4 numbers, right? But if we have a large enough sample size and we kept sampling, we approximate a normal distribution. And what's really neat about it is that this pattern, you find it all over life, right? For example, the rates of molecule change in chemistry, changes in human behavior after the manipulation of some independent variable. Even if you don't know the probability distributions of any of those things, which you likely don't, the central limit theorem tells us that if we sample from an existing sample and plot the frequency of those averages, we'll get a normal distribution that should reflect the parameters of the population. So there's 3 important things to point out here when we talk about these characteristics. The first thing is that your sample mean, right? Your sample mean should approximate your population mean. So this is under the assumption that the principles of the central limit theorem are true. So your sample mean should approximate your population mean. And the larger your sample, the more the sample mean will equal or approximate the mean of the population. Here it says equal. We don't literally mean that your sample mean is going to be an exact value that your population mean is. What we're really saying is that your sample mean should be awfully close. It should be a very good approximation of your population mean. And let's explore the logic of this a little bit, right? When we take a random sample, we expect that it's going to resemble the population, right? So we expect that our sample mean should be close to our population mean. But we've talked about sampling error, right? So we know that a sample mean might vary from the population mean. Remember that sampling error is just simply the discrepancy or the amount of error between a sample statistic and its corresponding population parameter. So in this case, Sampling error is the discrepancy between the sample mean and the population from which that sample came from. But and here's the kicker, right? We're not just talking about a single sample mean. Now we're talking about the mean of all possible sample means. So the central limit theorem states that the mean of the sampling means, right? So in other words, the mean of all of these samples, right? Particularly if your sampling rate is very high, the mean of all the samples should equal or approximate the population mean. Now, the mean of the sampling distribution of means may equal the population mean, but there's going to be some variation among all the different sample means, right? Remember, in the examples that I was showing you, of all the sample sizes 5 that I took, each one of our samples from our sample had a different distribution, right? They all looked different. And that's just by chance, right? That's the way it works in the real world. You randomly select some values from a distribution, and each distribution is going to be different in a way. There's going to be some variation. So in general, right, the sample means will tend to pile up around the true population mean, right? And the really off samples with extreme means, they're going to be fewer and far between. We would see that in the tails, right? And we see this in the histogram of the sampling distribution of the means. Again, most of our samples, what do we say? The mean was 3.8, and most of our samples pile up in the middle here, right? Around the mean. But just by chance, right, we get some samples that end up in the tails rather, of our distribution of sample means. And I mean, it may just be the luck of the draw, right? That we get a handful of samples that have a mean of 5, right? If we sample from that original distribution with a sample size of 5, and we're going to just end up with some that might have a mean of 5, or some that have a mean of 1. But chances are, if we have a high enough sample size, we're going to end up with a mean somewhere of around 3.8. So in order to reduce the level of error, right, we want a high sampling rate, a higher sampling rate. So this idea of your sample approximating your population data, it works best when we're talking 30 or more samples from our sample distribution. 30 or more samples. Now, because we're dealing with a sample of sample means of some size, right, meaning that we're now dealing not with just a single score, but some number of scores, right, that are taken from a sample and averaged together. Well, we can now calculate the distance that's expected between our sampling means and the population mean. And I'm talking about error that is expected simply due to chance. Now, once again, we're using samples to make predictions about populations, but we never expect a sample to perfectly represent a population. Now we're going to be able to calculate how much error to expect, right? This is going to give us an idea of how good or how accurate our predictions are. So in a sense, right, this equation that you see here that we're calling the standard error of the mean, right, in a sense, we're now calculating the standard deviation of the sample means, right? In a sense, we're calculating the standard deviations of this, right? So remember, standard deviation, that equals the standard or typical average distance between the individual scores and the mean, right? So standard error is the typical distance between the sample means and the population means. And we're not, I just want you to get the equation in your notes. We're going to do some examples here, but I want to tell you that, now that we're going to be dealing not just with one person's z-score, but with a sample mean, right? We're going to be using this equation in the denominator of our test statistic when we're computing z-scores. So we're going to do that for a couple of weeks now, right? So this is something we want to get used to. So instead of just the standard deviation in the denominator of our test statistic, we're going to compute something called the standard error of the mean, which is the population standard deviation divided by the square root of our sample size, right? So in a sense, you can think about this as a modification of the standard deviation formula, right? It's saying that the standard error, right, the difference in variability between our sample means and population mean that occurs strictly due to chance is basically, again, the standard deviation of our sample means. Okay. So here's a little hypothetical for you to think about for a second. What would be the standard error of the mean if we had a sample size of 1? So in other words, simply pulling one sample out of our distribution at a time, averaging it and plotting it, right? Well, it should be our population standard deviation, right? Imagine if we're able to sample one observation from the population until infinity, right? We'd end up with a perfect standard deviation for our population. So this is why the population standard deviation is in our equation here, right? It's our starting point. That is the absolute maximum amount of error that we might expect between a mean and our population mean. But of course, here's the rub, right? We're not going to be dividing this by the square root of 1 because we don't work with sample sizes of 1, right? So the amount of variability in a sampling distribution is always going to be less than the variability in a population because the extreme individual scores don't have an impact on variability of a sampling distribution. They've been partially washed out in the calculation of the sample mean. And this is reflected in the law of large numbers, right? Larger samples are more accurate representations of the population, right? The larger the sample size, the more probable it is that the sample mean will be close to the population mean. So the law of large numbers should make sort of some intuitive sense to you, hopefully, right? So if example n equals 1, like we see over here, maybe I'm lucky and I pulled a score that's actually the population mean. And likely if I did, if I did this one at a time for a small amount of numbers, so sample 30 times from a sample size of 1, I might have a standard error of the mean that's fairly high, right? Say 20, right? But if I bump that up to a sample size of 4, like we see here in the middle part of the graphic, I increase the likelihood of the average of those 4 numbers being close to my mean of 80, right? And if I sample, 4 numbers and I do that 30 times, my sample more likely starts to approximate the population mean. And my overall variability away from that mean decreases. And let's say I take 100 samples, I plot them 30 times, right? Then my sample mean has even less variability because of this high sample rate, and it is a better approximation of my population, right? So standard error is important. It's a measure of variability that gives us a single value that represents the average error expected between our sample means and our population mean. And when we're computing a z-score for a sample of scores, as opposed to just one score, the standard error of the mean is going to be our new denominator in our test statistic. All right, let's do an example. So suppose men's shoe sizes are normally distributed with a mean of 9 and a standard deviation of 2. What is the probability that a random sample of 36 males, the average shoe size is less than 8? Okay, so I want you to give this a try, right? I want you to pause the video, try and figure this out on your own. Now, remember, we're dealing not with a single score, right? We're not saying, okay, men's shoe sizes are normally distributed. What's the probability that one person will have an average shoe size of less than 8? We're not asking that question. We're saying, what is the probability that in a random sample, 36 men, right, will have an average shoe size of less than 8? So what's the probability if we randomly selected 36 men from the population, got their average shoe size? What's the probability that it would be 8 or less, right? That's the question that you're trying to answer here. And so you need to do a few things here, as you see on the slide. First things first, you need to compute the standard error, right? So don't forget that equation from the previous example here, right? You're going to need to compute the standard error because that's going to now go in the denominator, the bottom part of your z statistic. Once you have the standard error, then you can compute the z-score, right? In the numerator, the z-score is going to be the sample mean minus the population mean. So it's the sample mean minus the population mean divided by the standard error of the mean. And then you should sketch a normal curve, and you should label the location of the z-score. And then what you want to do is find the proportion, right? Find the proportion in this unit normal table for 36, the average of 36 men with an average shoe size of less than 8. So give it a shot, pause the video, and when you come back, I'll show you how to do it. Okay. So again, first you need to find the standard error of the mean, right? Well, that's nothing more than the standard deviation divided by the square root of the sample size. So if we take 2 divided by the square root of 36, we get 2 over 6, and we get a standard deviation of 0.33333 and so on, right? So we'll just round that to 0.33. Now we can use that to compute our z-score, right? Because that value is going to go in the denominator of our test statistic. So we're going to go sample mean minus population mean divided by that standard error of the mean that we just computed. And when we do that, we get a z-score of negative 3.00. Now, if I plot that here, right, here it is, right, negative 3.00. It's on the left side of the distribution, right? And let me go back to the question here. We're looking for the probability that in a random sample of 36 men, the average shoe size would be less than 8. So are we looking in the, we're obviously looking for a z-score in our unit normal table that corresponds with the correct proportion. But are we looking in the tail, the body, or mean to z? Well, hopefully you said the tail, right? Because this z-score of negative 3.00 represents the average of 36 men with an average shoe size of 8, right? So we're asking what's the average that, what's the probability that 36 men would have an average shoe size of 8 or less? That raw score corresponds to a z-score of negative 3.00. So we're looking for the proportion in the tail. So what we want to do is we want to find the z-score for 3.00, because remember these are absolute values because it's a proportional symmetrical distribution. If we then look at the proportion in the tail, it's 0.0013, right? So therefore, in a random sample of 36, the probability that the average shoe size is less than 8 is only 0.0013. Okay, so this is around the time where I would ask if you have any questions. Just sort of to recap before we continue on here. For any population with a mean and standard deviation, the sampling distribution of means for sample size n will have the following characteristics. Again, your sample should approximate the population mean. Your data should be normally distributed if it was normally distributed in the first place. If not, as long as your sample size is greater than 30, then the distribution of your sample means should appear to be normal-ish, right? And this standard error of the mean computes your variability for your sampling distribution of the means, and it is the value, is the equation that will go in the denominator of our test statistic. All right. So you'll be faced with questions, I think, at least on the homework, but maybe even on the exam, because we did something similar to this on the exam for individual z-scores. Here we're talking about what the shape, standard error, and mean would look like for a sample, right, coming from a specific population, right? So this is something that you want to sort of be able to wrap your head around here. So we've got these SAT scores that we know are normally distributed with a mean of 500 and a standard deviation of 100. So describe the expected characteristics for the sampling distribution of the mean when n equals 100. What would we expect the sample mean to be? What is our standard error of the mean? And what do we expect the shape of our sample distribution to look like? Go ahead and pause the video, answer these questions, and I'll give you the answers on the next few slides. So we'd expect our mean, our sample mean to approximate our population mean. So we would expect that to be 500 because that's the population mean is 500. Now note, here we've got a sample size of 100. And I want you to make sure you really understand this here. Even if our sample size was really small, right? Even if it was less than 30, right? We would still expect our sample mean to approximate our population mean. And this has to do with the idea of sampling from a normal distribution. Remember, we have the symmetrical normal distribution. 68% of our scores are within plus and minus 1 standard deviation of the mean. 95% of our scores are within plus minus 2 standard deviations of the mean. So the likelihood, even with a small sample size, that our sample mean should approximate our population mean is really quite high, right? If I were to only draw 5 scores at random from, say, this SAT distribution, and I took the mean of that, well, because the bulk of my scores fall close to my mean, there's a higher probability that I'll likely have a sample mean, even with a small sample size, that approximates the population mean. So don't let this n equals 100 fool you, right? Even a small sample size should closely approximate the population mean. That's our general prediction. The standard error of the mean is something we simply have to calculate, right? And to calculate that, we're going to take the standard deviation. Sorry, I'm getting all tongue-tied between standard deviation, standard error, standard this, standard that, standard oil. I don't know. All right. The standard deviation divided by the square root of our sample size. So 100 divided by the square root of 100 is going to give us 10. And the shape of this distribution, here's where the idea of sample size becomes important. Well, for one thing, you probably already know that this distribution was normal, right? Because we've talked about it before. But another way to even really reinforce this idea is that the sample size of 100 is greater than 30, right? Which is sort of our magic number here for we would expect a normal distribution for our sampling means. So we would expect our distribution for our sample to be, again, normal. Here's another example. Go ahead and I'll read it to you and then pause the video and give it a shot. The adjective checklist is a widely used personality test. Scores on the aggression subscale are positively skewed with a mean of 51 and a standard deviation of 9. Describe the characteristics of the sampling distribution of means for n equals 10 taken from this population. So pause the video, figure this out. So hopefully you said that our sample mean, right, should approximate our population mean. So you said our sample mean should be 51, right? It doesn't mean, again, that our sample mean is literally going to be 51, but we would expect that it should be a very, very close approximation of our mean, if not actually the mean. And again, notice the small sample size. It doesn't matter. Even with the small sample size, we still have a general expectation that our sample mean should approximate our population mean. Here we have to figure out the standard error of the mean, right, by taking the standard deviation of the population and dividing that by the square root of our sample size. That gives us a value of 2.85. And then lastly, the shape of this distribution is going to be positively skewed, right, because the sample size is quite small, right? In order for our sampling distribution of the means to take on a normal-ish shape, it either, again, has to originally come from a normal distribution, which this original distribution was positively skewed, so it didn't come from a normal distribution, or our sampling size has to be greater than 30. Here our sampling size is only 10, right? So in this case, our shape for our sampling means, distribution for sampling means, should also be positively skewed. Now look, if we bump this number up to something 30 or higher, right, then even though it originally came from a positively skewed distribution, because our sampling rate is high enough, we would expect the distribution of our sample means to have a normalish shape. Okay. Again, sort of the period in time where I would ask if you have any questions, but I can't see you raising your hand. Sorry. But of course, feel free to ask me. Okay. Let's do some examples. Let's do some SAT stuff, right? We've got, again, population mean of 500, population standard deviation of 100. What is the probability that a single student will get a score of 540 or greater. Okay, this is good. This is interesting, right? This is the way that we've been doing it since chapter 5, right? So this will really sort of illustrate the difference between what we did in chapters 5 and 6 and what we're going to do in chapters 7 and 8, and sort of really what we're going to do going forward, right? So this is just good old-fashioned taking a single z-score, or taking a single raw score out of a distribution of scores, finding out the z-score, and then in turn finding out the probability that a single student will get a score of 540 or greater. So a single student. So give that a shot. Pause the video, give it a shot, and I'll show you how I did it on the next few slides. Okay. So again, this is just computing a normal z-score, right? And here's our old equation that we've been using in chapters 5 and 6, right? So we know the equation for this is the raw score minus the population mean divided by the population standard deviation. So we get 40 over 100, and our z-score is plus 0.40, right? So we go ahead and plot that, right? In what we're asking here, what do I have to? Oh yeah, this would be me asking you. Should our probability be less than or greater than 540? Well, if you remember the question, it should be greater than, right? Because we're looking at the probability that the single student will get a score of 540 or greater, right? So 540 in this distribution corresponds to a z-score of positive 0.40. So we're looking for everything above this score, right? So we're looking in the tail. And if we do, right, we find the z-score of 40 and look at the corresponding value in the tail, right, we get a proportion of 0.3446. So given this distribution, right, there's a 34.46% chance that a single student would get a 540 or higher on the SAT. And that makes sense, right? I mean, it's close to the mean. It's, just shy of a half standard deviation above the mean. So, it's a fairly common score, right? It's not a score that would surprise us. Okay. Let's think about this a little differently, though. What's the probability that a sample of 16 students will have a mean SAT score of 540 or greater? So here's the thing. Everything that you just did, you want to do again, except now for your z-score, instead of the standard deviation in the denominator of your test statistic, you're going to compute the standard error of the mean. But then everything else is the same, right? You're going to get a z-score. You're going to plot that z-score on a normal distribution and figure out what you have to look up in the table to find the probability that a sample of 16 students would have a mean SAT score of 540 or greater. So again, pause the video, give it a shot, and I shall go over the answer with you on the next few slides. So again, here our z-score equation takes a different approach. In fact, that's actually wrong. While I'm here, I'm going to change that. That should be mean, right? That's the sample mean minus the population mean, and we're going to divide that by the standard error of the mean divided by we're going to divide that by the standard error of the mean, which is the standard deviation divided by the square root of n, right? So our sample mean is 540 minus 500, and we're going to divide that by 100 divided by the square root of 16. So now we get a z-score, right, of plus 1.60. And this z-score represents the average 540 for 16 students from this particular population. So now when we plot it, right, it looks like this. And the question we're asking is our probability less than or greater than 540? Well, again, just like the other problem, we're looking for the probability above this z-score, right? So a z-score plus 1.60 represents an average of 540 on the SAT for 16 people. So we're looking in the tail. So we're going to look up a z-score of 1.60, find its corresponding proportion in the tail, which is 0.0548. Right, so given this distribution, there's only a 5.48% chance, that the sample mean of 16 students would be 540 or higher on the SAT. So we have a high probability if we just pull one student that they get a 540 or higher, right? And that makes sense. That's common score, right? It's not that far from the mean. But a sample mean, a sample of the probability if 16 people, if we took their average and that average is 540 or higher, drops most dramatically to 0.0548, right? Which should, again, hopefully make reasonable, intuitive sense. And here's a few conceptual questions. You don't even need to do any math here. You just need to think it through. And you really need to just be thinking about the rules of the central limit theorem. Remember, if I have a sample size of 30 or greater, right, then the mean of my sample is more likely to approximate the population mean, right? So let's just deal with the question number 3 here. Who is more likely to have a mean SAT score between 520 to 530? And note that the mean is 500, right? So who's more likely to have a mean SAT score of 520 to 530? A sample of 4 students or a sample of 49 students? What do you think? Well, if I had a sample of 49 students, would the mean of the sample be more likely to be closer to the mean or more within the range of 520 or 530 compared to if my sample was only 4 students? The answer here is A. The answer is A. 4 students are more likely to have a mean score between 520 and 530 than 49 students are. And even if you understand this, I want to prove it to you using the math. Oh, again, my little equation is wrong. There we go. All right. So we're going to use, because we're dealing with a sample now, right? Sample size 4. We're going to use our one sample z-test equation with the standard error of the mean in the denominator of our test statistic, like what you see here. And what we need to do is we need to compute z-scores for both 520 and 530, right? Treating those as means, right? So 520 minus 500 divided by the standard error of the mean, right? Which is 100 divided by the square root of 4. Right, is going to give us a z-score of plus 0.40, whereas the z-score for a mean of 530 is going to give us a z-score of plus 0.60. And now when we plot these, right, remember what we're asking is what is the range here, right? What's the proportion in the range here? This is for sample size 4. So if we take everything from in the tail for our z-score of plus 0.40 and everything in the tail for a z-score of plus 0.60 and then subtract the smaller value from the larger value, it's going to give us this proportion right in between here that we're interested in. We did this several times in the last lecture, right, for chapter 6, and you did it several times on the homework for chapter 6 as well, right? So first let's just find these proportions, right? So the proportion in the tail for a z-score of 0.40 is 0.3446, and the proportion in the tail for a z-score of 0.60 is 0.2743. So if I subtract that from 0.3446, for sample size 4, the probability that the mean would be somewhere between 520 and 530 is 0.0743, right? 0.0743. Great. Now let's do the same thing, right? Let's do the same thing, except now let's do it for a sample size of 49. So everything in our statistic is the same as before, right? 520 minus 500. And we're dividing that by the standard deviation, which was 100. But now we're dividing that by the square root of 49, right? So that's going to give us a new standard error of the mean. And we end up with a z-score for an average of 520, a plus 1.40. If we do the same thing, figuring out a z-score for the mean of 530, we get a z-score of plus 2.10, right? Plus 2.10. And so again, our principles are the same here, right? We're looking for the proportion in the tail for both of these z-scores because we want to find the range between these two z-scores so we can find this proportion and that proportion and subtract this one out of that one. And here's the proportions that we get when we look it up in our table, right? So the proportion in the tail for a z-score of 1.40 is 0.0808. And the proportion in the tail for a z-score of 2.10 is 0.0197. So when we subtract them, boy, am I full of typos today. When we subtract them, we get a proportion of 0.062. 0.0629, right? So the probability, right, of a sample size of 4 students was 0.0743, and the probability of a sample of 49 students was 0.0629, right? So 0.0743 is a higher probability than 0.0629. So it's more likely that a sample of 4 students would have a mean SAT score between 520 and 530 than a sample of 49. In question 4, it works the same way. We're not going to do any math for question 4 because, again, it's hopefully pretty intuitive to wrap your head around. Who is more likely to have a mean SAT score between 490 and 510? So in other words, note here, a mean SAT score really right tightly around the mean. Would it be a sample of 36 students or a sample of 100 students? The answer is B, a sample of 100 students, right? With a larger sample size, even though 36 is a fine sample size, 100 is even more, right? So the larger your sample size, the more your sample mean should approximate your population mean. So we would expect with a larger sample, the mean of that sample should be more close to the population mean than the mean of a smaller sample. Okay. There's a question on the homework, kind of weird, but you need to know how to do it. We don't do it very often. In fact, I wouldn't be surprised even if you took on a career as a scientist, you may never do this, but nevertheless, it's still something that we teach. You can determine the number of subjects in a study if you know the population standard deviation and the standard error of the mean. And you can calculate n by this simple equation, right? You're going to take the standard deviation divided by the standard error of the mean, and whatever that is, you're going to square it, right? So how many subjects would we have in a study with a standard deviation of 20 and a standard error of the mean of 10? Go ahead and pause it and figure it out. Figure it out using this equation. So we take our standard deviation, 20, divided by our standard error of the mean, and square that. That's going to give us a n of 4. Let's try another one. How many subjects would we have in a study with a standard deviation of 15, standard error of the mean of 3? Go ahead and give it a shot. Yeah, so 15 divided by 3, that's going to be 5. If we square that, it's going to give us 25. So again, sometimes you do work backwards. Sometimes if you're reading somebody else's paper and you have questions about sort of the sample size, although typically papers report the sample size, so it's sort of a kind of almost an anachronistic sort of thing. But there's a question on the homework, and you'll have to answer it. I promise you. I'm more than happy to say this is not going to be on the exam. So just know it for the homework and don't really worry about it. Okay. So for those of you that are going to sort of go on and take a research methods class, you'll note that, or maybe even those of you that take some classes where you've had to read some psychology papers, right? You might see bar graphs reported or time series data reported with the error bars representing the standard error of the mean. And that's often a mechanism of how we report variability of sample means in a paper, right? Typically, you don't report the standard deviation, but you report the standard error of the mean. Another method is something that we call intervals, confidence intervals, which is something that we're going to be learning in a few weeks. Either convention is fine as far as APA is concerned. You can use standard error for your error bars, or you can use confidence intervals. I tend to use confidence intervals. I think it's just sort of a matter of personal preference. But the nice thing about you using something like standard error bars here is that when you glance at a figure, right, not only do you get a picture of the sample means, right, but you also get an idea of how much error you would expect, right? So it's a nice sort of visual function. Okay, so that's it for chapter 7, right? So here are some questions from the back of the chapter, and of course, if you have any questions, don't hesitate to let me know.